So if you're going to work out a problem like this one, how do you do it? The first step, as always, if you are trying to go towards Thevenin's equivalent circuit, is to identify your load resistor. The load resistor is the resistor you're trying to analyze. In this case, you're analyzing the 20 kilo ohm resistor. That is one which is going to be our load. And it's the resistor between the terminals A and B. Now, how does it work? Once you know where the load resistor is, you want to reduce everything else in the circuit to just one resistor, the Thevenin's equivalent resistance. One power source, a voltage power source connected in series with the Thevenin's resistor. This is going to be the Thevenin's equivalent voltage. And then connected to the 2 points A and B. And then afterwards, you can bring back the load resistor. So this is what is going to be the Thevenin's equivalent circuit. So this is what we want to do. So everything else from here up to there, everything here has to be compressed to just one resistor and one voltage source. Now, what do we do? In the presence of a dependent source, we actually don't go right ahead to find the Thevenin's resistance. We have to take an in-between step. We have to get it indirectly. So how are we going to do that? The first step is still the same. We need to open the load resistor. So we will draw the circuit without the load in place. So to do that, of course, you will have to redraw the circuit. Perhaps let me just make the redraw. Okay, so you open the load resistor. So the load is the 20 kilo ohm resistor this side. So when it is opened, it means that we remove it from the circuit. The circuit remains like this. So what we now want to find is the voltage across the two ends in the absence of the load, or the two ends where the load was connected. So this is the V open circuit. The open circuit voltage is the one that will take us the V Thevenin. Now, what is going to be our V Thevenin, our V open circuit? We see that in the absence of the 20 kilo ohm resistor, the voltage across A and B will be the same as the voltage across the 5 kilo ohm resistor. So you have to see that in this case, to find the open circuit voltage, all we have to do is to find the voltage difference across that 5 kilo ohm resistor. To find the voltage across the 5 kilo ohm resistor, since what we have here is a current supply, so it's supplying current in this line. So this is the current that will be passing through the 5 kilo ohms, meaning the voltage used by the 5 kilo ohm resistor, voltage by the 5 kilo ohm, this will be equal to the current that will pass there. Since the dependent current source there is the one supplying the current, and it's supplying 0.01 V0 current, so we'll multiply this by the resistance there to get the voltage drop across the 5. So we'll convert this back from kilo to ohms. So this will be 5,000 ohms. So that now the two decimal places will deal with those two zeros, giving our expression for V across the 5 kilo ohms to be equals to 50 V0. So this is the voltage drop across the 5 kilo ohm resistor. And remember, this is our V open circuit. Once we have the voltage drop across the 5 kilo ohm resistor, or our expression for V0, V open circuit, we realize that we need to know V0. So again, V open circuit and V0 are separate, so don't confuse the two. I think I just made that. So we need to find V0 if we're going to know our V open circuit. And what is V0? The dependent source is the one that defined V0 for us, but we see that V0 is determined by the voltage across the 10 kilo. So to determine the voltage across the 10 kilo, again, since this is a current supply or a current source, it's supplying 5 milliamps. So the 5 milliamps in terms of current is the one that will come to pass through the 10 kilo ohms. So to find the voltage used by the 10 kilo ohms, voltage used by the 10 kilo ohms, which is V0, will be equal to the current that will pass there, which is 5 milliamps, multiplying the resistance there, which is 10 kilo ohms. Here we see the milli and the kilo will do opposite to each other, so they'll cancel out. So we're just multiplying 5 and 10. So 5 by 10 is 50, giving us V0 as 50 volts. So once we have the expression for V0, we can now easily get V open circuit. V open circuit will be 50. Where there's V0, we'll put 50 as well. 5 and 5 give us 25 with those two zeros in place. So this becomes the value for V open circuit. Once we have obtained our V open circuit, remember V Thevenin is the same as V open circuit, which is 2500 volts. Now we want to find our Thevenin. But to find our Thevenin, like I pointed out, we are going to use an in-between step. What we're going to do here is we are going to find the short circuit current. So where the load is, this time we'll remove the load again, but this time we will short it. So we'll replace the load with a short circuit. What we now want to find is the current that will be passing through where that short circuit was. And we'll label this as I short circuit. Now we're doing this because you see the open circuit voltage and the short circuit current have got one relationship. If you used Ohm's law, it turns out that the V open circuit is equal to I short circuit times the resistance. The resistance that you obtain here is actually going to be the Thevenin's equivalent resistance. So from here, since we already have the V short circuit, open circuit, since we already have V open circuit, we'll just divide this by the I short circuit. This will give us the resistance that would be associated with that line. So this is mostly what we'll be using in such a case. Another approach that we could have used, instead of just keeping it short circuit or open circuit, we could have included a test supply, a test source. Now this test source would have given us, if we are to insert a test voltage, then we'd put that test voltage here, and our goal would be to find the corresponding current, which would be what would come here to determine the corresponding resistance. We'll use that technique as well with another problem so that you see how it works. But for now, for problems of this nature, we just short the load to find I short circuit. So if we short this, what will be the current that will pass here? Now with the short in place, you have to see that when the dependent source here supplies 0.01 volts, 0.01 V0, when that is supplied here, as long as AB is a short circuit there, no current will take this route. If this was a lamp, it will be off because no current will go there. All the current will go towards the short circuit. Current takes the easiest path. So all the current goes towards the short circuit. In other words, this 5 kilo ohms will act as if it is not even there. Our circuit will remain like this. What does this mean? All the supplied current, the 0.01 V0, all of it will go to pass through AB. In other words, I short circuit will be equal to the supplied current 0.01 V0. Notice that even direction here is the same because this dependent source is applying current that is flowing this way, more like clockwise. Even current across this, we're labeling it to say it's going clockwise. If it was that the dependent source was applying current going downward, would have said that they are in the opposite direction, would have concluded that I short circuit is equals to negative of 0.01 V0. However, for our current problem, they are in the same direction. So we will leave it like that. But the other side, notice that the absence of this resistor here hasn't changed anything. For this circuit, we still have the voltage V0 equal to the 5 milli multiplying the 10 kilo. In some problems of this nature, you find that the absence of this will affect one of the terms this side. So be on the lookout for such questions. Here, nothing changes. So the milli will still cancel with the kilo, giving us 5 by 10, giving us 50 watts. So whenever you withdraw this, don't always assume that nothing changes here. I would always encourage you to still come and analyze this and see if something changes. For this one, nothing has changed. V0 remains 50. So when you get I short circuit, we have 0.01, where there's V0 we have 50. So we see this becomes 0.50 amps. So having found our I short circuit, now we're going to come to this expression. The Thevenin's equivalent resistance will be V open circuit. The open circuit voltage, we found that. Note that the open circuit voltage and the V Thevenin, they are the same. So we have 2500 volts. Then we have I short circuit, which we found as 0.50 amps. When we divide, we get our Thevenin as 5,000 ohms. In kilo, this becomes 5 kilo ohms. Once that is done, since we now have Thevenin and V Thevenin, we go back and complete our Thevenin's equivalent circuit, or you can redraw it. So for Thevenin, we have found Thevenin as 5 kilo ohms. V Thevenin, we have found V Thevenin as 2500 volts, or you can write it as 2.5 kilovolts. That is also fine. So this becomes the Thevenin's equivalent circuit.